Hello and welcome to my I think fifth video in Transformers, and now in this video I'm going to show you what is a practical transformer. So this is going to be a little bit harder to understand than in the previous videos. I hope I'm doing a good job. So this is I think gonna be a longer video, and I'm gonna use this book to explain it a little bit better. So now in my not previous but two videos before this one, the third video, I think that I explained, or it was the second one, I explained what is an ideal transformer. Now you know that when something says ideal in engineering, that doesn't exist in real life. So in that video we saw what are the ideal characteristics for us with transformers. Now, and we said there were two characteristics. One, there was no resistance. Two, there was no flux leakages. And three, the permeability of the magnetic core is infinity. So now we're gonna see what is the real or practical transformer. So all windings, every winding, every conductor has its own resistance, and therefore the windings you see on these transformers have a resistance. You know that the resistance is equal to the specific resistance times the length of the conductor divided by the area of the conductor. Now, but for a better look, we can put this resistance in series with this winding. So R2 is in series with this winding over here and this over here. So this R1 and this R2, those are the winding resistances of the transformer. So we put a resistor here as I always use this rectangular for a resistance. If you use this symbol, you can use this one. So that is, for me, it's easier to use this resistance. So we put the resistance of the winding in series with the with this winding, and here. So those are the resistances. Now that is one practical characteristic. So every winding has its own resistance. If it isn't a superconductor, but we don't have superconductors for transformers, I think. That's not something that I found it on the internet or any use in electrical machines. So all conductors have some resistance. Now, the second characteristic on an ideal transformer was that the flux here produced on the windings are all obtained on that magnetic circuit. Now that's not the case. Although this flux M goes through this, obtains both of these windings, there is a flux leakage in the primary and the secondary winding. So all of this current here produces some flux leakages, and we can some of this current has an inductance leakage, which is equal to inductance leakage L in index L1 is equal to L1 times the flux linkage of the primary divided by the current I1. Now, this inductance we can put in series with the winding over here as a reactance of this flux linkage. So current I1 and current I2 in both these windings produce some flux linkages. So that's why we rarely use this core type, and we always wound the windings one on another so that the magnetic flux linkages are minimized. And the inductance of this flux linkage is by this formula. Also, the inductance on the secondary side is pretty much the same formula, just we use number 2 as index. And all this, and you know that the reactance is equal to 2 pi times the frequency times the inductance. That's in physics. You learn this in physics and electrical engineering. And we, this inductance of these linkages, we put them in series with this winding and with this resistance of the winding, both on the primary and on the secondary side. Now we have here we have a tightly coupled magnetic field over here. So now in order us to calculate and measure all of this, the resistance and the inductance, we put them aside, and we have here a tightly coupled transformer with turns ratio of N1 divided by N2. So, but here this is not an ideal transformer. We want to make it an ideal transformer. So all of those losses, all of those parameters, we how do you say it? Put them aside, like here. But I'm gonna explain it now. So the second characteristic was that the second ideal characteristic was there were no flux linkages, but in real life there are. So one of these flux L1 and flux L2 go in the air. So that's we can't use them to magnetize the magnetic core. They go in the air, and unfortunately for us, that's a bad thing. But usually these things are very, very small, and this here resistance and this reactance of the flux linkages have small values. So yeah, that's it. Now the third characteristic of an ideal transformer, in my second video, I said that we said that the magnetic core has an infinite permeability, so there is no exciting current in that ideal transformer. Well, that's not the case, and if you watch my magnetic circuit lectures, in the 17th video I showed you what is the exciting current, and to magnetize the magnetic core, the magnetic circuit, we need that magnetizing current. That magnetizing current is drawn from the supply, but because we always have hysteresis losses and core losses, and in order to have a sinusoidal magnetic flux in the core, we need to have an exciting current. So I hope you learned that in the it's very hard to learn transformers if you don't know the chapter of magnetic circuits. So now we're gonna draw the equivalent circuit for a practical transformer if we take that the permeability is finite. It has a value, which of course every practical transformer has a limited permeability. It doesn't go to infinity, unfortunately for us. So here we had the resistance of the windings and we had the reactances of the flux leakages. So we want this to make an ideal transformer. You'll see why. We said that there is an exciting current, and in order for us to draw that on the schematic, and if you remember from the magnetic circuit, this here, R index C1, is the resistance of the core loss in this magnetic circuit. Magnetic circuit. And here is the reactance of magnetizing this core. So this XM1 is for this flux M. So this is looking from the primary side. So these are the core losses, and this is for the magnetizing this current. And here we have I flux 1. So here is I flux 1 going like this, and it goes to other branches. I C1, and it goes to I M1. So this is the current for the core losses, and this is for the magnetizing the circuit. And you know that IS is in phase with the induced voltage on the windings here, and you know that IM is perpendicular to it, and the exciting current is something like this. And we do that, we calculate it with the Pythagoras theorem. Now, as you can see, this is usually very small, and it's hard to calculate it, but you'll see in my next videos what are the tests performed to calculate this and this. Now, as you can see, the supplied voltage V1 and the induced voltage, so this and this, now look at it, are different values. Now, as you can see, there are some voltage dropouts on the resistance and on the reactance of the flux leakage here, and E1 is usually a little bit smaller than V1 in real life, but you'll see later on that we can transfer this to the other side. But okay, now okay, so I don't know what to say anymore, just gonna remove this. Now, and now we have an ideal transformer with the ratio N1 divided by N2, the turns ratio. And all of these parameters are the resistances and the reactances of this of the transformer. And this, all of this here and here, you calculate using some experiments. Some test measurements. And we'll see them in my next videos. Now, what do we want to do? We want this to move left or right, because we want to have a better picture of this transformer. Now we can move it from the left side to the left side, but we have to do that impedance transfer on the right side, from the primary to the secondary, all of this. Or we can move this ideal transformer on the right side, but we need to transfer this resistance and this reactance on the primary side, so we can have a better equivalent circuit. And I'm going to do that by transferring this ideal transformer on the right side, and we're gonna do the impedance transfer from this side to this side, and we're gonna do the voltage transfer from this side to this. So I'm just gonna remove this here, so I will have more room to draw the equivalent circuit. Because impedance transfers are very useful for us, and it's easier to do the calculations. Now, I said that we want to transfer the ideal transformer on the right side. Then we need to do the impedance transfer from the secondary to the primary. So this part here, let me just look, stays the same. So I'm gonna, I'm just gonna copy this part. So we have V1, we have the resistance of the transfer of primary winding, we have the flux leakage reactance on the primary winding. Now we have this here. This is the exciting current parameters. So okay, now we have a primary current that goes like this. We have an exciting current that goes like this. We have a core loss C current, the current for the core loss here, and we have a magnetizing current over here. Now, if you want to move this ideal transformer on the right side, we need to do the impedance transfer from the secondary to the primary. And we just put this the prime over here, and like this. And the induced voltage E1 and E2 are the same. You'll see why. So this is the transferred voltage from the secondary to the primary. And the current I2 is now I2 prime. Okay. Now we have the V2 transfer to the primary side, and then we have an ideal transformer over here that goes to the load. But we are gonna also do the we're gonna transfer this side on this side. So we have here a current I2, and we have to the induced voltage V2. Okay. Now what have we done? We made an impedance transfer from here to here, and XL2 prime is equal to A squared times XL2. R2 prime is equal to A squared times R2. This is the impedance transfer. Now the voltage transfers, when we transfer the voltage, it usually stays the same. And if you want to transfer the induced voltage, we also do that on the same. So basically the voltages are the same. If you transfer the secondary to the primary voltage by that impedance transfer equations, you get the same voltages. V1 is equal to V2 prime, and A1, oh no, sorry, the A1 is equal to A2 prime, and yeah, V2 prime is equal to A V2, because you know that you have to trust me on this one. I forgot to. Sorry, I just realized the book didn't cover this one. So this is the transferred voltage from the secondary to the primary. If you want to transfer it from the primary to the secondary, then E1 prime would be E1 divided by A. So just the opposite. But if you have impedance, then you have A squared. But if you have from the secondary to the primary, and if you have voltages from the secondary to the primary, you just have A and A, not A squared. Okay, now, and yes, the current I2 prime is equal to I2 times A. So we do that. So now the circuit here is much more, how do you say, electrically readable. But there is one more problem here. We need to transfer the load on this equivalent circuit, and that is very easily done. And now I'm gonna do that over here. I'm gonna remove this circuit here. And here we have a connected load, Z2 prime. No, sorry, just ZL. This is the load connected on the secondary of the transformer. And if we want to transfer this on this circuit, this is also secondary to the primary, we just use this formula. Because now if you transfer this to here, then the equivalent circuit is much more, it's much easier to determine all these parameters, and it's easier to determine them, and when you know what is the XL2 prime and R2 prime, you can easily calculate the original values of this of the secondary parameters. So now we have, if we want to transfer this from the secondary to this equivalent circuit, now we have here the induced voltage V1. Now we have the resistance of the primary winding. Now we have the reactance of the flux leakage. Now we have the resistance of the core, reactance of the magnetizing the magnetic circuit. Here we have the flux leakage reactance on the secondary, but the transferred value from the secondary to the primary. That's why we put this prime over here. Now we have the transferred value of the resistance of the secondary, and we have now a transferred impedance of the load on this primary side. Now looking from the primary side, now this is the equivalent circuit. Looking it from the primary side, you could do that all on the secondary, but this is more commonly used. Now the induced voltage from here to here is equal to E1 times E2 prime. The current here is I2 prime. The current here is I1. And usually I1 is equal to I2 prime because the current, the exciting current is 5% of this, usually about 5% of the primary current. Here we have IC1, here we have IM1, and here we have V2 prime. And now this is the equivalent practical equivalent circuit of the practical transformer looking it from the primary side. And I want you to know this circuit. This is very important to know, and it's very this is now the equivalent circuit of the transformer looking from the primary side, and it is very hard. We can measure it, all of these parameters individually. I don't know, you can put an ohm meter to measure the resistance, but it's hard to measure the reactance of the transformer. It's hard to measure this and this individually, and this is very hard to measure, and that's why there are some tests that are performed to do that are called the no-load test and the short circuit test. Now, one more circuit here. Okay, so this is the practical transformer equivalent circuit. Now we have resistance, we have reactances, and also resistance and the load. In the ideal transformer we didn't have this and this. But in real life we have these parameters, and as an engineer you have to calculate them. Now, if the resistance and the reactance are small, which they usually are, E1 here, the induced voltage on the windings, that here is E1 is pretty much the same as V1. The supplied voltage is almost equal to the supplied voltage. If that is the case, which it usually is, we can transfer this R1 XL1 on the we can transfer R1 and XL1 on this branch here, because the voltage drop out on the resistance and the reactance, but you know we don't have dropouts on the reactance, that's reactive power, but the voltage dropouts on this impedance over here is very, very small, and if that is the case we can transfer this to the other branch. Now we have an equivalent circuit like so. Now we have V1 Now, if these are very small values, we can transfer this on this branch. So the E1 is equal with V1, and which is equal to E2 prime. So from the voltage induced on these points are equal to V1, and that is usually the case because in the transformer we have a small resistance of the winding, and this is a very small value. The reactance of the flux linkage is a very, very small value. Now we can put R1. Oh, sorry. Now, if we take if we take this circuit, if we use this circuit, it's much easier to calculate these parameters like this. I don't get this book. I don't know why they do that, but okay, this is not. Well, this circuit is much more accurate than this one, but yeah, but it's better for me to say something about this in my next video. So sorry about this, and now we are going to do some tests. I'm gonna show you what tests are used to determine all of these parameters. So stay tuned, watch my next video, and yeah, this here is going to be much more easy. It's hard to this is a long video. It's hard to say anything more. So just look at this for now, okay? I'm gonna explain this over here in the next video. So see you in my next video, and I'm gonna show you the no load test. See you around.